Okay, I'm just going to keep on plowing through examples of using Fourier transforms of some kind to solve partial differential equation boundary value problems. We've already been through 2 examples. Here we'll do the third one. Remember, the first thing is to figure out which variable to take the transform with respect to, and then which of the 3 transforms do you use. Here, both variables, well, here's the partial differential equation. Here, both variables come as second derivatives, so we can't narrow it down there. But the range of x is finite. It's just from 0 to pi, but the range of y is semi-infinite. It's everything greater than 0. So we're going to take our transform with respect to y in this case instead of x. And since it's semi-infinite, we know it's either going to be the sine transform or the cosine transform. So we look at the initial condition for where is y 0. Here it is. Here's where the condition where y is 0, and it's on the derivative of the function. By the little rules I laid out earlier, that means we use the cosine transform. Go back really quickly. Here were my rules. So if it's semi-infinite, you know it's one of the either the sine or cosine transform. And then you look for the initial condition of whether it's on the function or the derivative of the function. What was it in our case? Well, in example 3. On the derivative, so we use the cosine, just like those rules said. So in this case, since we're taking a transform with respect to y, this second derivative is just a plain old second derivative of the big U with respect to x. And then for the y, that's where we go look it up on our formula sheet if you don't remember it. And it was this, minus alpha squared big U minus U sub y. But in this case, U sub y was just 0. Well, that makes it nice. So here is our ordinary differential equation. Notice the minus sign here. This is a standard equation we've seen multiple times in this course. It has this general solution for when the extent of x or the range of x is finite. We use the quotient sines instead of exponentials. So here is the general form of the transform of the solution, actually the cosine. Now we need to find big A and big B. We'll be using these other boundary conditions. Here's our solution so far. Here's the boundary conditions remaining. Let's look at this one first. The transform of this guy, since we took it with respect to y, is just going to be big U with x equals 0. Here's big U. If I plug in 0 for x, sin is 0, cosh is just 1, so it's just a. That equals cosine transform of whatever that function is, it's just 0. That tells us a equals 0, so this is what our big U looks like after applying this condition. Now we'll take that solution and plug in pi for x. This side, b sin alpha pi. Big U with the argument of pi for x, it has to equal the cosine transform of this. Plug that into the definition of the cosine transform, and it's this. So we have to evaluate this integral. I use the Laplace trick, and here it is. So b equals this divided by sin alpha pi. Plug it back into here. Here is our cosine transform of the solution we want. So we get the solution itself, we just take inverse cosine transform. There it is. Do one more example in this video. See, in this case, we know we're going to do it with respect to x because it's the only one with the second derivative. It is indeed semi-infinite, so we know we're either going to use the sine or the cosine transform. Let's see. Do it with respect to x, so we're looking for the condition where x is 0. It's this guy, and it's on the function itself, not its derivative, so we'll be using the sine transform. Hence, in this case, we're going to encounter this ordinary differential equation that we encountered a couple of examples ago. And you don't have to evaluate this integral. I just say, here it is. But these things will crop up as we solve. We're going to take the sine transform with respect to x. K times minus alpha squared. This thing can be put on your formula sheet. It's in this same briefing. On the right side is just d big U dt. Together in one ordinary differential equation. In this form, it gives you the answer in that form. Again, this K is different from that K. Sorry about that. But if you can make that translation, here is the solution to this ordinary differential equation. Now we need to find big A. Where we are. Here's where we were so far. Here's the condition left to go. Right? We just have one more condition. Yeah, we used this condition. Showed up on that side. So what do we have here? Look at with respect to x, so we plug in 0 for t. When we do that up here, this is a 1. We just have big A plus 1 over alpha. That has to equal the sine transform of this boundary. Is this. So we know what A is. A is this minus 1 over alpha. Add an all one thing. Here's what big U is now. It's this A. Just putting in this for big A. That to this. And now all we need to do is take the inverse transform, look it up on our formula sheet, plug in the above in the formula. Save this example for another record.